This is 0.85, right? One little piggy goes this way, right? This current is 0.58, or 5.6, is that right? Yeah, 5.6 repeating, right? And then this current here is 0.283 repeating, right? But don't they flow together? Didn't they come from the 0.85? Don't they flow together again to form a 0.85? Don't they? It's a river. It's the river. The river splits and goes around an island and then comes back together, yes? The current before the island and the total current after the island is the same, unless there's like a tributary or something like that, yes? Yes, this is, by the way, one of Kirchhoff's laws. One of Kirchhoff's laws, the second of his laws, or the first, I don't know, right? Okay, is that the sum of the currents flowing into a junction equal the currents flowing out, yes? No, the current never goes away. You could, if you add resistance, the total current goes down, but you never create or destroy electrons, right? Because they're matter and they're conserved. Okay. Okay, so now we know the current through and the voltage across all the parts of that. Are there questions about that? Let's do a harder one. Let's go to the next page.
That's exactly what I was thinking.
Oh no, looking at that I could see it, I mean it's just perfectly clear. Okay, let's see if this pen works. Da-da-da. Do I have that one the same? That's correct, isn't it? All right. That's a good one. All right. That's polite for shut your pie holes.
When's convenient?
Anytime. I don't know. It's up to you. Can we be quiet, please? All right. So this one, I think we've done this, right? This is 15, isn't it? Right? Please calculate along with me. So I know that we overwrote our memory location. So now we've got to like store these guys, right? And then this one is 1 over, so I'm doing this, I'm reducing the circuit until it's solvable, right? So 1 over 1 over 11 plus 1 over 15, okay? And I'm going to store that in A, so 1 divided by 11, storage A. So that's A is 6.346. And now it's solvable. I don't need to reduce it all the way down to one little nugget, right? I now recognize that this is a simple series circuit, yes? It's this guy, this guy, this guy in series, right? Okay, so I'm going to solve that. I'm going to solve that series circuit. Okay, so I'm going to go 22. The current is 22 divided by 5 plus A plus 9. Can we chatter a little less? Yes, sir. Yeah, go for it. And I'm going to store that in B. Okay. So 22. Has everybody stored this number, the result of that calculation, in A? Yeah, please do this as we go. This is what you need to learn. So 22 divided by parenthesis 5 plus alpha A plus 9. And I'm going to store that in B. This is a very important thing. That's B as 1.081285 da da da. Okay, this is amps. Okay. And then I'm going to go and I'm just going to solve. The next step is to just solve things that I can solve. This ammeter right here just reads that current, so it's 1.08 amps. That is the current going through that one. Yes? It's the current going through the 5 ohm, it's the current going through the 9 ohm, and then of course it splits up and does crazy stuff there, right? But I can solve these things. This voltmeter here, I'm going to use IR, right? So it's going to be 1.08 or whatever, right? I'm going to use the letter B times 5, right? So I've stored that in B. Have you stored that in B? Because if you haven't stored it in B, it won't make no sense when I say that it's B times 5, right? So I'm going to go times 5. That voltage is 5.406. I'll say 5.41 volts. Yeah? This voltage here is also going to be IR, right? And the current I've stored in B, so I'm just going to go B times 9. So alpha B times 9, and that's 9.73. Right? Okay. And that's volts. So now we know the current through those things. We've totally solved this part of the circuit. The current through this and this one is 1.08128 or whatever, right? Okay. On both of those. And the voltage across this one is that. The voltage across this one is this. We're almost done. But we're not quite done. We still need to find the voltage across the reduced part, this thing. Okay? Let's find that voltage. Well, that voltage is also going to be IR. Okay? So the reduced voltage, the reduced resistor, the voltage is going to be I times R. I stored the current in B, and I stored that total resistance apparently in A. Is that right? So that is Ba, right? And the numbers I'm using here are 1.08125 or 1.1285, etc., right? Times, and then A is 6.346. But all I have to do on my calculator is go alpha B times, times alpha A. And I'm going to store that in C. That is 6.862 8620037 blah 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 blah, right? Okay. That is my voltage. Had there been a voltmeter across that part of the circuit, right? Had there been a voltmeter across from here to here, that would be what it reads. But we don't have one, so we don't have an answer to put down. Yet I still need to do this one, right? Now I'm set. Now I need to pop it open again, right? So now I'm going to, yeah.
Could you just subtract the V1 and V2?
Yes, indeed you could. Indeed you could. Okay. Okay. So now the next thing looks like this, right? The voltage of this one is 6.862, and I stored that in C. Right. Okay. Dot dot dot. So dot 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 means I'm going to use a more precise value of it. Now we've got a circuit that is like this, and this is not a very hard circuit, right? And then I've got